Welcome to PIQ'S TV. This is another lesson under General Chemistry 2. This is your host, Dr. Glenn Michael Jameson Pitero. Our topic here is all about chemical complexes, or most commonly known as the coordination compounds. So, what are chemical complexes? These are structures formed when molecules bind together, typically involving a central atom or ion surrounded by molecules or ions called ligands. This session will introduce you to different formation types and its importance. What are chemical complexes? Chemical complexes, often called coordination compounds, consist of a central atom, metal, or ion bonded to surrounding groups of molecules called ligands. These ligands can be neutral molecules like water or ammonia, or ions like chloride or hydroxide. How do we form chemical complexes? Chemical complexes form through coordinate covalent bonds where both electrons in the bond come from the same atom, typically the ligand. This unique bonding gives complexes their stability and interesting chemical properties. So in the previous lessons, we have learned about naming common chemicals. This time, we're focusing on the nomenclature of chemical complexes still under IUPAC. Let's have the first example here. Let's have some concepts first. The name of a complex ion includes the name of the central atom and the ligands. The ligands are named first, followed by the metal. If the complex ion is an anion or something which has about a net negative charge, the name of the metal ends with ate as the suffix. So it's very important to take a look first on the formula of a coordination compound or a complex. Let's have example 1. So it involves iron, then cyanide with a subscript of 6, and the overall net charge is negative. So let's apply first. Let's name first the ligands as the first step. It's called the cyanide ligand, so it would be cyanido. Then name the metal. Iron is the central metal here. Since it's an anion, so it has a negative 3 charge, it would be named as ferrate instead of iron. The overall name here is the hexacyanido ferrate 3, where hexa indicates the number of cyanide ligands and 3 indicates the oxidation state of this particular iron. So how do we get the oxidation state? It's just 6 plus negative 3. So it would be, yes, that's the oxidation state of iron. So it would be positive 3. So let's now have example number 2 involving chromium and ammonia. Let's name first the ligand. So it's a slightly complicated coordination compound. The ligands are ammonia, so it would be amine, and water, it's aqua, and that's the two ligands here. So the net charge is positive 3, so we don't have to name it as chromate. It's still a chromium. So since it's a complex cation, the name of the metal remains, or it will not change. The overall name of this coordination compound is triamine triaqua chromium 3, with tri indicating the number of each type of ligand in the coordination compound. So we have 3 ammonia ligands and 3 water or aqua ligands. So it's triamine triaqua chromium 3. How do we get the oxidation state of ions? It's just So the subscript is 3 here. So for the amine, it's 3. So 3 plus 3 is 6. So actually, it's -6 for both the ammonia and the water. So -6 plus +3. So it would be 3. 6 minus 6 minus 3 is 3, +3. So it would be triamine triaqua chromium 3. Now talk about the type of ligands. We have actually 3: monodentate ligands, bidentate ligands, and the polydentate ligands. Let's talk about first the monodentate ligands, wherein the binding is at a single site, like water and ammonia, and also including cyanide, chloride, and the pyridine. Pyridine is connected to the formation of the DNA and RNA for the nitrogen bases. While for the polydentate, we have the famous EDTA, or the more stable ligands, the polydentate. Since there are multiple sites for ligands to bind, so another example is diethylene triamine. So let's take a look at the monodentate here. So there's one binding site here. Here for the water, it's oxygen. Then we have the nitrogen here. Then in terms of cyanide, it's the central atom of cyanide. And for the chlorine, monodentate, and pyridine here. Well, for the bidentate, we have here this is the first ligand attachment and the other ligand attached to another CH2 molecule here. So we have two attachments, so it's a bidentate ligand. So that's how we classify ligands in terms of the number of attachments. So in terms of simple problem solving, it usually involves identifying the geometry of complexes. So if we can remember the VSEPR, you can look it up on the previous lessons. Consider the complex or the coordination compound involving nickel and ammonia with a charge of +2. Nickel here is surrounded by 6 ammonia ligands. So according to the VSEPR theory, for those having um, a domain of 6 or number of electron groups, it would be under octahedral. It has 6 ligand bonding sites around nickel. So on your notebooks, you can try to name this particular complex here. Just disregard here, it's NH3, it's still ammonia with a subscript of 6. The coordination compound here, net charge is positive. To try to name this particular formula or coordination compound. Chemical complexes have vast applications, from the vibrant colors in ink and paints to the catalytic processes in industrial synthesis. They are also crucial in biological systems, such as the heme group. So the heme in your hemoglobin, which is important for cellular respiration because it binds oxygen in our blood. To conclude, chemical complexes are a central part of inorganic chemistry with implications across many scientific fields. They demonstrate unique bonding and properties that are pivotal in both technological applications and essential in biological functions. Okay, we are now at the end of our video lesson. Just like our previous video lessons, we have our own exit cards. Just write the things or conclusions about what you have learned about the topic, and also what questions are you going to ask the teacher. You can post this in the comment section of our YouTube video. Laging tandaan, sa PIQ'S TV, panalo ang natuto.